Good afternoon all. Welcome to today's Samvaad-Talk. The theme for this series is cryptography and security. As you all know, the speaker of the day is Professor Srinivas Vivek. Dr. Srinivas Vivek is currently an assistant professor at IIIT Bangalore. He was part of the postdoctoral research. He was a postdoctoral researcher in the cryptography group at University of Bristol, UK. He has obtained his doctoral degree from University of Luxembourg, master's from IIIT Bangalore, and his bachelor's from NIT Surathkal. His research interests are in the design, analysis, and implementation of countermeasures against side channel attacks and homomorphic encryption schemes. I, on behalf of IIIT research community, welcome him to share his insights. Welcome you, sir.
Yeah, thank you, Anjana, for the kind introduction, and thanks to Professors Jaya and Ashish for the well organized Samvaad series. Of course, special thanks to Professor Srinath, the founder, head for all of this talks. And it's also heartening to see that at least the strength in today's Samvaad, it's like at least a couple of times than the strength like it was last year when I gave the talk. So good, so that's good. So yeah, so let me get started. I know that there are many cryptic terms. So yeah, this is cryptography, but still the title itself sounds cryptic. So basically what we do is, so very recently in 2018, the researchers from IBM India Research Lab in Bangalore, and then researchers from IIT Kharagpur, they proposed a cryptographic protocol, and we showed that it is not secure. So this is what cryptanalysis means. So that's a formal way of saying. So a less formal way of saying this is we broke the protocol, okay? And probably even more informal way of saying, but surely popular term is we hacked the protocol, okay? So so this is joint work with Shyam Murthy, who is currently doing his PhD with me. So I did offer him a chance to present this, or co-present this, but then he was happy to listen, to sit on the other side. So yeah, other terms I'll explain, during the course of the talk. And there's no prerequisite needed, to listen to this talk. So the problem setting is, so suppose we have a client, okay? It could, for instance, be a cell phone, and then it has outsourced, some data set to a server, okay? So nowadays outsourcing is, cloud computation is the fashion, right? And because the cloud, the storage and the computational resources that are offered at very cheap price, so we try to offload, our data and computation as much as possible. Okay. So client has given a server a data set. For instance, it could be the set of emails. So we don't run email servers on our phones, for instance, right? So we use the services by Google. So and then I'd say at some point the client has a query, okay, and then it wishes to determine assume that S consists of some points, okay? I'll give you an example shortly. And then Q comes up with a query, the client comes up with a query point, okay? Then it wishes to determine the nearest neighbors for this query point, okay? So when I say nearest, I'm using this notion of metric, some notion of distance. Okay, assume there is a metric there. So for a given query point, you can tell what is the shortest, neighbor in the data set S, and then so on. So when I say k nearest neighbors, okay, so probably the k points in S that are closest to Q, okay. So just let me give you an example, okay. Suppose the set S consists of some points in the xy plane, okay. So there are a pair of coordinates, okay. So and there are say n points, okay, and then suppose the distance metric used is the Euclidean distance. So when the client comes up with a query point Q, okay, so then and if say k is 1, then basically you are just computing the nearest point in the set S. to the point Q. Okay, clear? Is the problem setting? And then now I'm glad that I brought this sentence early in the talk. So hopefully, looking at the term machine learning, many students in the audience will be even more motivated to listen to the talk. Okay, so apparently this computing k nearest neighbors is a basic primitive in machine learning and data analytics. So probably the experts there, am I right? Okay. Yes. But then there's a problem. Okay. What about the privacy of the outsourced data? Okay. Okay. So you are giving the data in all clear. Okay. So then there's a possibility that your server can steal the data. Okay. Or figure out what you are doing. Okay. So there's all sorts of possibilities. So how can we avoid that? Okay. And that's a concern, right? Yeah. So one of the means to achieve this privacy is through encryption. Okay. So and let me stress, before I tell what encryption is, let me stress that this is only one of the means. So for example, in the current currently the most popular way to ensure privacy is to sign some legal contracts. Okay, between the client and the server. Okay. So if server tries to misuse it, and then so then it has to go through all the legal proceedings. Okay. But we know that particularly in our country, that the legal process can be quite consuming, right? So basically, so in this talk we are looking purely for a technological solution, okay, that ensures the privacy of the outsourced data. Okay, so encryption is a cryptographic primitive. Okay, so where a plain text, okay, a data in the clear, okay, that is gets transformed into what is called a ciphertext. Okay, on input possibly a secret key. Okay. So here in the picture, what you see is the text of an inscription from the 5th century called the Halmidi inscription. So that's the first inscription available for the Kannada language. So here when I put it in the red frame and put a lock, so what I mean is that the text has got encrypted into a ciphertext. Okay, and the property the encryption schemes must satisfy is, if I don't have access to the decryption key, then I will not be able to learn even one bit of information about the underlying plain text. Okay, and then yeah, so as I said, so this figure, I mean there are two types of encryption scheme. One is called the public key encryption scheme and the private key encryption scheme. So in a private key encryption scheme, you just yeah, so you encrypt and decrypt using the same key. Okay, just like, so those schemes work like our traditional lock. You lock and unlock with the same key. Okay, but in the public key encryption scheme, you use like a number lock. You possibly we can encrypt. You can encrypt with a publicly known key, and you can decrypt with only with a secretly known key. Okay, so plain text upon input a public key. I'm just in this figure illustrates a public key encryption scheme. So plain text upon the input recipient's public key gets transformed to this ciphertext, what you see here, and then upon on receipt, the recipient inputs his or her private key, and it gets transformed to the original plain text. Okay, and as I said, others means those who don't have the decryption key cannot learn anything about the underlying plain text. So coming back to our k nearest neighbor problem, so basically, so the client will encrypt its data and send it to the server, and then even the query point, it can encrypt and send it to the server. Okay, so usually any communications over the internet, so it will always happen, because you use a public medium, right? So there will be encryption, applying at the lower level. But what I mean that is that the server still will not have the decryption key to recover the plain text from the data set plain text or the query point. Okay. Okay. Is it clear? Any questions so far? But then encryption and outsourced analytics. Okay. So basically, the server is trying to do analytics on the outsourced data set, right? What the data set it has got it, but then so encryption and computation on it are seemingly contradictory. Okay, because because the server does not know the secret key, I mean, there is no way you can try to do anything meaningful with it. Okay, so these are contradictory requirements. So privacy and outsource analytics are contradictory. Probably I think the privacy should have been the apt term here than encryption. So privacy and outsource analytics are contradictory, and it turns out that a typical encryption scheme does not support computation on encrypted data. Okay, so how should we go about this? It turns out that some very cool and recent primitives called homomorphic or fully homomorphic encryption schemes, they allow this possibility to compute on encrypted data. So where one who is computing on the encrypted data will not know the secret key, it can perform meaningful computation on the ciphertext. Okay, without learning anything about the underlying plain text. So just to give you an example, so suppose you encrypt some plain text that's equivalent to say 1 rupee, okay, and you have another plain text that's got encrypted. Okay, now without having the secret key, and because I put a red rectangle box and a padlock, it means they are all ciphertext. They are not the plain text information. So you can still, without knowing the key, you can add to ciphertext and get the ciphertext of the sum. Okay, it will not know what is the value sitting inside, but still it would have one with this fully homomorphic encryption schemes can produce the sum of the ciphertext. Means encryption of the sum of the messages. Okay, it's possible, and then you can even multiply to ciphertext. Okay, without knowing the decryption key, and yet you can form the ciphertext of the product of the messages. Okay. So, and this was invented a decade ago by Craig Gentry when he was a PhD student at Stanford. So the story goes like this. So when his supervisor, Professor Dan Bonnet, gave him this, in the class he mentioned about, then it was an open problem, how to do this, fully homomorphic encryption. So why I say fully homomorphic encryption? Because, previously the schemes were known that support only one type of operation, either addition or multiplication. Okay, so probably many of you would have heard of the RSA encryption scheme, that is multiplicatively homomorphic. You can multiply two ciphertexts and get the product ciphertext without actually decrypting it. Okay, and then a well-known additive encryption scheme is the PIA encryption scheme, where you can add two ciphertexts without knowing the key, and you can get the sum of the ciphertext. Okay, but then doing two together, so if you can do addition and multiplication, you can think addition as XOR, okay, and multiplication as AND. So these two together are universal, right? So moment you can realize addition and multiplication, you can do any computation. So Dan Bonnet then suggested this open problem, and then Gentry solved it, and he got his thesis. Okay, and he also got the ACM doctoral dissertation award for this. So solution, yes. Mm-hmm. No. So okay, those data that are those ciphertexts that are corrupted, only that information will be given out. Rest all what is not corrupted will be intact as it is. So you can view it as, okay, so you are computing a modified function, okay, so where some of the data are in the clear, so rest all are encrypted. So it would reduce to that setting. Oh yeah. Right, yes, yeah. Yeah. No. So what I'm saying is, so this you can reduce to an instance where the known values are given in the clear, rest are all encrypted. So you are just computing a different function. That's it, nothing more than that. Oh no, I mean, what do you mean by mathematical basis? So it's all based on some hard problems. So what are the hard problems? So they come from their. So there are some hard problems in ideal lattices. Okay, and there is something called approximate common GCD. So there are some mathematical problems that are assumed to be hard, and if they are really hard, so then these schemes are secure. So these schemes, so those mathematical problems, they provide kind of basis for the security of these encryption schemes. If they are not hard, for example, you know that RSA is based on the hardness of integer factorization, right? But then if you can solve integer factorization, then RSA cannot be secure. So similarly, there are some other problems in lattice-based problems. So if they are hard, I'll not get into the details. So there are some mathematical structures. So regularly they are. Oh, this is another lattice. So not from the Boolean theory. So this is something. So this is from the geometry of numbers. So where they are regularly placed grids, and you are trying to find the shortest or the closest vector. So yeah, again, yeah. So we'll not get into the technical details, and we can talk offline. So this fully homomorphic encryption schemes, they provide that primitive, right? So here, so the data set, outsourced data set is also encrypted. The query point is also encrypted, but not using traditional encryption scheme, but using fully homomorphic encryption schemes. So there are also other competing technology like multi-party computation, but here, so we want to do it completely non-interactive. Means the client will just give out all the data and ask the server to do it. So there in those settings, so fully homomorphic encryption schemes are useful. But then, okay, so in order to use a fully homomorphic encryption scheme, so you need to represent a circuit as consisting of addition and multiplication gates, because they are the native operations that are supported. Okay, so for example, as I said before, you can view this plus as an XOR gate and multiplication as an AND gate. Okay, so inputs are given. So inputs. So first, you try to represent this computation over plain text, and then the same circuit can be used for computation over the ciphertext, where the inputs, some of the inputs can possibly be encrypted. So basically, you are trying to represent the entire computation as a Boolean circuit or an arithmetic circuit or a field. Okay, whatever that means. So okay, so then, so natural question is, okay, there are already schemes like fully homomorphic encryption scheme. So then why we are not encrypting all our outsourced data? Okay, why our Gmails, why still Google is able to read our emails and then give us targeted ads? So the whole business is run on this, right? Because it's giving targeted ads. So that's how they are generating their revenue. So it's because the current the technology is actually too inefficient to be deployed in practice. To do a full-fledged deployment, it's very, very slow. Okay, so it's about so on paper they're all so for a theoretical computer science it's efficient because it all runs in time polynomial in the size of the inputs. Okay, so here input is the level of security, well, security parameter, but then in practice it's about 1,000 to more than million times slower. So for example, if you want to just XOR 2 bits where both the bits are encrypted, the resulting ciphertexts are a few megabits or megabytes. Okay, yeah, you need that for the security. Otherwise, if you compromise on that just for the efficiency, then the adversary will be able to break it. Okay, so but then so what is the bottleneck is the multiplicative depth of the circuit. So basically, how many AND or the multiplication gates are in series, that is the multiplicative depth of a circuit. So the longer the depth, the higher the depth, so then more inefficient is it. So in fact, it kind of increases, like drastically with the multiplicative depth. Okay, but then it's not all bad. Okay, so still, it's feasible, it's efficient in practice, okay, to evaluate low multiplicative depth. So those computations, okay, for which the depth of the circuit is not too large, so those schemes can be, those circuits can be efficiently evaluated on the ciphertext homomorphically. So, and in fact, there are many startups, and we have one startup here called the Zero Labs. Okay, so they are running a successful business. So that means, I mean, they also into homomorphic encryption. So that means that so efficient in practice, to be deployable, but provided the depth is not too high. Okay. So just one technical point. Okay. So why multiplicative depth matters? It's because for the encryption happens like this: the plain text gets modified, and there will be some noise component, okay, additive noise component, okay, to make it all secure. And this doubles upon addition, but it squares upon multiplication. So the moment it reaches, the noise reaches certain threshold, so then the decryption will not work properly. So that's the reason. But of course, that's not needed for the current talk. Okay. Yes. Oh no. Yeah, as I said before. So there is the encryption happens by adding some noise component to the cipher, to the plain text. Okay, the cipher text is generated, okay, by adding kind of. I'm not trying to be too precise. So the message gets added with some noise. That noise doubles upon addition. But say suppose you have a plain text. Yeah. Yes. Yeah, it's in series. Yeah, when you have consecutive multiplications. Yeah, the sequence. Because the noise gets squared upon every successive multiplication. Okay. But if you have in parallel just one multiplication, so then it's not a problem at all. It's only the sequence, consecutive multiplications, the cause of all the problem. So yeah. So this fully homomorphic encryption schemes allow the possibility to evaluate any number or any circuit. Means it can have any number of addition gates, any number of multiplications, and whatever structure. But then if you restrict, the encryption scheme, or you design or you parameterize the encryption scheme to support only small depth circuits just for the sake of efficiency, then it's called somewhat homomorphic encryption. Okay. So just to add to the Gentry story, so when he submitted the paper to STOCK is the Symposium on Theory of Computing. So which is a premier conference in theoretical computer science. So a reviewer pointed out that so your scheme is not fully homomorphic encryption, means you cannot evaluate arbitrary circuits, but only somewhat homomorphic and only some limited depth, multiplicative depth circuit. So and then he had only a little time to change. So then he came up with a breakthrough idea, which is at the core of his breakthrough. So where he could convert somewhat homomorphic encryption to fully homomorphic encryption scheme. So not that we should send something to a conference in a hurry and then wait for the reviewer to point out, but in this case it happened. It worked out well. Okay. So in order to apply the homomorphic encryption scheme in practice, so we just need to look at somewhat homomorphic encryption schemes, because only those are currently efficient in practice. No, efficiency just in running time, nothing more than that. Okay, not even talking theory. Sorry. Yeah. I'm not talking from a theoretician's perspective. Here I mean efficiency is practical efficiency. So whatever runs in seconds or minutes is okay, or maybe few hours, not more than not few years or few decades. Okay. Oh, but in 10 years there's a lot of improvement. So probably people could not have implemented Gentry's, the original proposal. But in 10 years, so much work has happened. Now this is the current state. Who knows? In next decade or two, probably we'll all be encrypting all the data with our source. You never know. So okay. So in this context, okay. So coming back to our so we cannot simply use a fully homomorphic encryption scheme, because when we try to see the first step when you want to do the computing the k nearest neighbors is to sort the data, right? Sort the data. Even in order to sort the data, you should first implement comparison. Okay. Suppose there are 16-bit words, so that the multiplicative depth, when you try to write the comparison circuit as a Boolean circuit, okay. So depth itself will consist of say 16, okay. If you do it in an I way, okay. So then that itself is too slow, you cannot afford, okay. And then you want to compare, do several comparisons, okay. okay, then probably it will become, so, and in fact the best, the record data, number of data that sorted homomorphically is about, runs into 100, So, so if we want to sort, say, few thousands of data, it would take, few hours or few days. So it's not at all efficient, okay. So in this context, Kesarmani and others at, recently, so they published this work at EDBT. EDBT is the extending database technology, I suppose, okay. 2018, they proposed a solution, a very efficient solution to compute k nearest neighbors, okay. So they did not employ a fully homomorphic solution. So they used somewhat homomorphic encryption schemes, and then they had some other tricks, and and they could handle very large data sets running into more than 100,000. So they could do it efficiently in a few minutes, okay. And then not that the previously researchers have not considered alternates to fully homomorphic solution. It's just that they are better in terms of efficiency, both asymptotically and in practice. Okay, I'll get into the details of it, but I just want. So, for example, so on 200,000 data points, okay, and you have a query point. Say, just suppose say k is 1, where you are computing the nearest, okay, and a point. So they could do it in just 2 minutes, okay. And of course, as k increases, time will increase, but still 8 minutes is not too large, okay. So yeah, so this is the reference to the paper. So let me quickly go through the protocol. So you have a client, you have a server, okay, and then they assume another server, okay. So they do it in a 2-server setting, okay, and they assume that server A, server B are rival, they do not collude with each other. Okay, there's a reason for that. I'll come to it shortly. Okay, so client has a secret key, okay, and that's going to share it with the server B. Not very impressive, but yeah, again, but yeah, but so for example, A and B can be rival, they can be business rivals, and hopefully they don't collude with each other, because if the server B, so if the server B shares the secret key with server A, so then there's no privacy achieved, right? Okay. So and then the client is going to encrypt the data set, homomorphically using somewhat homomorphic encryption schemes, okay, and then say probably it would have at some point it would have sent the encrypted data set, and at say a later point of time it comes up with a query point, and it wishes to compute the k nearest neighbors of the query point Q in the data set S, okay, such that both server A and server B will not learn anything, okay. So usually server A is not the problem, as long as the underlying encryption scheme is secure, server A will not learn, we can be safe that server A will not learn a lot, but then because the server B is actually the real adversary, because it has access to the secret key, okay. So it's going to client is going to send the query point, okay, and then okay, so it will compute the distance, okay. So for example, the distance, say let's assume that let me give you a quick example, okay. So for example, the S can consist of, say here in this example, 3 points. So there can all be pairs of coordinates, say in the xy plane, okay. It could be even n points, okay, in general. And then so, and this, I mean, there's no restriction that Q has to be only tuples of 2 elements. It can be even d tuples. We don't like, it doesn't matter. So if Q is the query point, so then it just computes the Euclidean distance, okay. So computing this is not costly, because you just need one multiplication, right? You need to subtract square, okay. You need to subtract square, okay, and add it. So it's just a depth 1 multiplicative circuit, and we can very efficiently compute this. It's not a problem, okay. So when I meant d, so d is the that distance, the Euclidean, the square of the Euclidean distance, is what is computed, okay. Okay, and then what it does is it picks up a random polynomial with integer coefficients, okay. So means that polynomial is monotonic, okay, and the coefficients are all randomly chosen, say from some range, and the degree of the polynomial is not too large, and then the square of the Euclidean distance are transformed through this random polynomial, okay. So let me give you an example. Suppose you pick up a degree d polynomial. So what they suggest in their protocol is db9, okay, because degree cannot be too high, because remember all these operations are happening on ciphertext, not on plain text. Okay, so ciphertext, I mean, you evaluate this polynomial because the coefficients are positive. Okay, and then your inputs are also not negative, right? Because you compute square of the Euclidean distances. Okay, so the order is preserved, but what they expect is the polynomial values themselves do not give out a lot of information. So only the order is maintained. So suppose if x3 is bigger than x2, bigger than x1, assume. Okay, so then because this is a monotonic polynomial, so even the order will be preserved, but the actual values will be kind of randomized. Okay, so then the hope is, okay, so this is sent to the server B. Okay, and it's in what order the ciphertext sent, it doesn't matter. In some random order, it's permuted order, the ciphertexts are sent, because each point in P of D is a separate ciphertext, or it could be many ciphertexts. Okay, so it's not that whole thing is compressed into one ciphertext. So each distance what is computed, it can be in one or more ciphertexts. Okay, or it's usually one ciphertext. So there will be n ciphertexts if there are n points. So now, okay, so that is sent to the server B. Okay, so now, okay, so server B receives the encrypted, transformed distance. Okay, and then it's going to decrypt it. Okay, so look, now I have taken out the box and the lock. So it's decrypted because it can do the decryption because it has the secret key. Okay, so the belief is, because only the date of P of D, okay, where the square of the Euclidean distances are transformed through a random polynomial. Okay, so it will not leak anything other than just the order. Okay, because sorting is needed, right? First you need to sort and then compute the k-nearest neighbors. Okay, so and then it's going to sort. Okay, it can do because they are in plain text. You can quickly sort as many elements as possible. Okay, and then it is going to compute the indices of the k nearest neighbors. Okay, and it's going to send back to the server A. So it's going to receive the indices. Okay, and then it had permuted the order, right? So it's going to apply the inverse permutation because it chose the permutation to apply. Okay, so and then it's going to sorry, I'm going back. Okay, and then it's going to give it to the indices and possibly the corresponding ciphertext also to the client. Okay, so in the process, server S will not learning much except the order of the indices, but it will not learn the actual points because it's all encrypted. So again, as I said before, the adversary is the server B. It's expected that it will not learn anything other than the order of the Euclidean distances. Okay. Okay, as I said, yeah. So this is the server B is the adversary to look out for. Okay. So here the transformation happened through a random polynomial of degree D. So D could be 9, and they are all positive integer coefficients. They can come from some range. Say for example, the coefficients can be 16-bit coefficients. Okay. So okay. So why it's integer polynomial? Because so currently the homomorphic encryption schemes can basically handle only integer like data. Okay, even if you have floating point value, essentially you need to scale it to an integer, in order to do the computation. That's why we assume that the polynomial have only integer coefficients, and it's also evaluated. Even all the points are represented as integers. Okay, and in fact, in my previous Samvaad-Talk, I talked about why it has to be integer. So any other scheme, like there are mainly two schemes to represent the fractional point numbers, and they are all equal, and that's what I spoke in the last Samvaad. So here we just assume it for now. Yes. Oh no, as long as the polynomial has positive integer coefficients, it will be. No, it's the distance. Yeah, x1, x2 are the distance. Okay, the squares of the Euclidean distance. The moment the polynomial is has positive integer coefficients, it will only increase. It's pretty obvious, right? The least value it will take is a0 when you evaluate at 0. Next step, it will be sum of coefficients. Then it will only increase. So this is definitely monotonic. Yes. No, then client will essentially doing all the computations, right? It needs to sort, it needs to determine indices. So then arises philosophical question: why in the first place even outsource data? It can sort, because sorting is comparison and sorting is the bottleneck. Okay. So now, yeah. So to give the example of what all information server B has, because first we should understand the capability of the adversary, right? So before trying to see what all it can do. Okay. So it knows the degree, because these things can also be part of the protocol description. Okay. It knows the degree. Okay. Or even if it knows the degree, it knows it has to be small, because it understands the limitations of the homomorphic encryption schemes. Okay. So they suggest degree 9, and then number of points it knows. Okay. Because it would have received as many ciphertext, for instance, and the range of the coefficients. So alpha. So they are all alpha bit integers. So they recommend alpha to be 16. Okay. And beta can be small. Usually for many real world applications, you don't have, you need to handle, encode them as integers of, really huge size. Usually, typically, it will be small. Okay. Okay. So yeah. And then, of course, after it decrypts the p of xi's, the square, transformed square of the Euclidean distance, it knows these values. So it knows the degree, knows the number of points, it knows the coefficients. It also knows that probably the coefficients are randomly chosen and they are positive. Okay. Okay. Alpha. And then probably it knows also where the inputs come from. Not the exact value, it will not know the xi's, but it knows the output, polynomial output values. Okay. So what they claim in the EDBT paper is server, okay, with these parameters, it will only be able to recover the input, the distances, and eventually the polynomial with only probability 2 power minus 160. Means there are 2 power. So just given the polynomial outputs, no inputs are given. So there are possibly 2 power 160 polynomials, that take on this value. Okay. So that's what their argument is about. So basically, their argument is based on the fact that number of variables is greater than the number of equations. So may not be sound formal, but there are other reasons to believe that. Okay. I will not get into technical, the deep technicalities. Okay. So basically, yeah. So remember, there are endpoints. So each x1, x2 are the square of the Euclidean distance. Okay. So p is the positive, where all the coefficients are randomly chosen and they are positive. Okay. So they claim that always you have d plus 1 more equations than the number of variables. Okay. So that's why they think that you cannot recover it. Okay. So in fact, yeah. Okay. So in fact, even we are not aware of previous works that recovers polynomial from only inputs. The well-known Lagrange interpolation. Okay. So for that you need to give the input-output pairs. And also polynomial recovery is also has like very interesting connections to decoding the error correcting codes. Okay. So there also you should give input-output pairs. Everything should be given, and some fraction can be noisy. Means the output may not be you could have got the output corrupted during the transmission. So but then just recovering polynomials from output only. So we are not aware of any work that has addressed that. Sorry. Oh yeah. So we have, that's a very good point. So we have modeled our attack along this. This is one of the means. So huh? No, it's all homomorphic, right? And it's fast, probably,
That's not the only.
Yeah. Of course, yeah. But there is, okay. If you permit me to, write it. So if you solve this, so here we are assuming integer coefficients and and integer inputs, right? But you can prove that, very formally prove that, if they're all real numbers, okay? So then there are in fact too many possibilities. So basically what you are given is the outputs, right? Say p of x0, p of x1, so on, in some, they're not in that order, in some, so n points you are given, okay? Suppose you choose a0 to be very small. So in fact you write any polynomial, okay? then there will always be an intersecting point, and there will always be a root, right? So for any output, so given any polynomial, provided that the constant coefficient is not big, for any polynomial, you can always, given the output, so any polynomial can take these output values, because you just need to find the corresponding points, okay? So in fact, it's not totally incorrect. Is this point clear? Yes. Yeah. Yes. Yes.
Can I still be able to solve the KNN problem?
That's a good question, but I don't know. So I'm not. Yeah. So, but in the first place, how would you learn?
Machine learning.
Okay. Yeah, machine learning. Yes. Yeah. No, that's a very valid question. Yeah, but I'm not aware of that. If it is, if it is really practical. So yeah. Yes. Oh, monotonous is increasing on. No, because so I have some inputs, I transform it to the outputs, right? But then the order should be the same. Otherwise, I cannot sort it. So server B is going to sort it and return the k indices, right? The order should be maintained. That's why it has to be monotonic. Yes. Yeah. Oh, you want? Oh, yeah. There are some schemes called multi-key homomorphic encryption schemes. So on paper you can do, but again they are even to implement they are very, very inefficient. Even lot more inefficient than these schemes. But that's, yeah, you're right. So you can possibly. So what Professor is asking is, so if we encrypt different ciphertexts using different keys, still you can operate. Yes, it's possible. So probably there are n parties. You encrypt using n keys. Okay. So still on paper you can do it, but again they are even inefficient than encrypting with just a single common key. Okay. Yes.
The WhatsApp is supposed to be linked.
Yes. Yeah.
Say if I make a group in the WhatsApp.
Yeah.
And I send a message.
Yeah.
How is it? Is it same encryption for all the recipients? Different encryption for different recipients? How is it then resolved?
That's a very good question. So I should confess that I don't know the answer. Probably what I suspect is for every pair it's encrypted differently. I think so. Yeah. I'm not sure about that. Yeah, but yeah, I'll try to figure it out and tell you the answer. Good. So just to quickly recollect what is Lagrange interpolation. Suppose you are given 3 points. So you can very efficiently construct the a degree 2 polynomial that fits these points. If you are given d+1 points, then you can efficiently construct a degree d curve, a polynomial that will fit through the d points. Okay. So if we want to, again, we cannot naively, we can use Lagrange interpolation because we only know the outputs, right? We don't know the inputs. So basically, if you want to apply Lagrange interpolation, you need to guess all the inputs. But the inputs, they are all beta bit inputs, right? So there are 2 power beta possibilities for each of the input xi. Okay. So then you need 2 power beta power d+1. Okay. So if you assume that d is 9 and beta is 16, even if the inputs are encoded as small integers, you still you want to naively apply Lagrange interpolation. You need to make 2 power 160 trials, which is too large. So believe me, if for the current day security, even if you ensure that your adversary needs 2 power 80 steps, then you can assume that with the current computing power, your scheme is secure, your protocol is secure. Okay. So basically, I think this problem itself may not be interesting. Problem of recovering polynomial outputs, polynomial inputs or the polynomial only from the outputs may not be even interesting, theoretically, because so there are many equivalent possibilities. So for example, okay. So suppose you have a curve, a polynomial, okay, So then you just try to shift the coordinates, okay? So x, I am trying to make it x plus 2. So then I got another polynomial. So this will have a different equation, right? But it will take the same outputs, right? Because it's the same polynomial, okay? So possibly you cannot recover the polynomial uniquely, okay? Because they're all equivalent to, affine shift, a linear shift, or up to differences, okay? But in our setting, luckily we can, we could recover the polynomial uniquely, okay? So here, say for example, yeah. So C got displaced, the coordinate got displaced by 2 units. So suppose your polynomial took values at x1, x2, x3. For the new polynomial, it's going to set the same value at x1 minus 2, x2 minus 2, because anyway you are adding plus 2, right? Good. So here next we, will show our, so we show that, we present a method to recover all the distances and eventually the polynomial, okay? And our attack works for small input space. So up to 32 bits, we show that our attack is feasible. Yes. Yes, to hide the inputs. Yes.
And the reason we want to hide the inputs is we assume server B has access to the data set.
To key, yes. To the key. So it knows the inputs, the square xi's are the square of the Euclidean distances, right? Yeah. No. But you see, and suppose it has some a priori information about the query point, Yeah. So we are not trying to completely, reconstruct the set S or the set Q. That may not be difficult because it only up to distance we made, but that itself is locking a lot of information, right? And remember, in crypto, the attack only gets better, so. No, not in this paper, But again, even if it learns the distances, it's considered a breach because it's not supposed to learn anything more than the order, right? So our attack works in mainly two steps. So look at two polynomial equations, okay? So the first observation is if you take, and they're all integers, okay? And in fact they are non-positive integers, okay? The moment you subtract, okay, assume that x2 is greater than x1 because on looking at the order on the p of xi's, because it's monotonic, it will know the order on the xi's, right? Okay, so I can safely assume that x2 is bigger than x1, x3 is bigger than x2 because server B will be able to determine that. Okay, so now the moment you subtract, you see that the constant term goes off, right? Okay, and then the I term will be ai into x power whatever, x1 power I minus x2 power I minus x1 power I, means x2 minus x1 is a common factor. Okay, so I can pull it out. So rest all I don't care. Okay, and note that, okay, x2 minus x1 should be less than 2 power beta because each of the xi's I know is less than 2 power beta, right? So what the first step is, take p values, they are known to the adversary, right? So compute the difference, okay, and factorize, okay, compute all the factors, okay, up to 2 power beta because you know that x2 minus x1 is one of the factors. Okay, so what we'll do is, so it will not determine the exact value of x2 x1 nor the exact value of x2 minus x1. So what it will do is it will try to generate possible guesses, because they're all the guesses constitute all the factors of p2 minus p1. Okay, p of x2 minus p of x1. Okay, and then of course we need to repeat it for so d minus 1. So we have to repeat this process d times, right? Because remember, to apply a Lagrange interpolation technique, it's enough that we guess only d plus 1 input points. So then you can recover the degree d polynomial. Okay. So basically I'll fix x1. Okay. So the smallest value, then I compute p of xi minus this and all the factors up to 2 power beta. Okay. So this will constitute the guess for x2 xi minus x1. Okay. And I have d equations and x1 will be the free variable. Okay. So remember I showed that plot that you can only recover up to the differences, right? So this is because of this reason. Okay, up to differences. Okay, yes.
That strategy works to perform all computations over some finite field or because
oh no, I don't think so. It's all integer. So factoring, we use the factoring, right? It has to be integer. So I told you, if I real data set, then the scheme is secure. If it is properly real quantities, then their scheme is secure. But it's only we exploit the fact that, so basically if I want to go back this figure, so there probably they made a mistake that, if the intersect is going to be there will be any solution, but actually when it intersects it has to be integer solution, okay, because the inputs and outputs are integer. So this is what we exploit and we can reduce the search space from 2 per 160 to 2 per 30 or 2 per 40, which is really feasible, okay. So yes. Yeah, because that's the limitation of a homomorphic encryption scheme. Even if you take a floating point value, it will only have finite precision, right? So and then ultimately you represent in the FHE world, you represent any floating point as just a scaled integer. I can represent 3.4 as 34 into 10 power minus thing, right? Yeah, so that's the point. Yeah. So the moment I collect D equations, so I just need to plug in values for x1. Need to guess it will be 2 per beta values, okay. So just note that, and it turns out that, I cannot just take the values plus D values, okay. So I cannot take x2 to xd plus 1. It cannot simply work like that, because sometimes there will be too many devices, okay. The moment my guess set becomes large, okay, then I need to try, so for example, if there are say some T1 choices for the, x2 minus x1, there are T2 choices for x2 minus x3 minus x1, then the number of enumeration space will only be, will be product of that, right? So if I put psi as the limit for the number of devices, then if you have D equations, then you need to enumerate psi power D, okay? So that's already expensive, and it turns out that there will be too many devices, the psi can become very big for small values, okay? So in fact, there are some number theoretic results that gives you bounds on the number of usually you expect log, if you have a number n, you expect log many divisors, but there can be, it can even be sub-exponential, okay. So we'll learn. So you need to look at so many values, okay, and then come up with only those xi's, because ultimately you just need some D, D plus 1 points. It's not that it has to be x1 to xt plus 1, it doesn't matter, okay. So in our computation we restricted psi to be 10, okay, and then number of points it turns out to be just 40, so n should be much bigger than the D, means number of points should be much bigger than the degree, but for degree 9 it's enough we have 40 points, okay. So as I said, the next step 2 is just apply Lagrange interpolation. There's one free variable, right? Run through every possible value of x1, that will fix all the D plus 1 inputs, outputs, then compute using Lagrange interpolation compute, and check if it's consistent with the remaining n minus D minus 1 points. That's it, okay. So that is an expensive step, and it takes 2 power beta enumerations. Remember psi power D, and for every psi power D you need 2 power beta. Maybe you can even, I was only so far fixing x1, I was just looking at the columns, and see ultimately I need D independent equations. I was looking for a column, but it can come from the whole matrix, okay. It turns out that this problem reduces to finding up the least set of the optimal set of D equations, okay, turns out to be related to the problem of finding minimum spanning tree with only D edges, okay. So that's an interesting connection. Oh, in fact that problem turns out to be NP complete, but there are approximation algorithms, and Professor Mulidara pointed out this results on minimum spanning tree. So thank you for that. So this is an optimization sum, that's not important for our thing. So we can work out, doing the exact analysis is difficult because we cannot compute the number of devices, it's quite difficult, okay. In fact, the number theoretic results are on randomly number of devices, expected number of devices for randomly chosen integers, but they are all coming in from a polynomial, right? So they are not necessarily random, okay. So we just do some loose, not a tight heuristic attack, and complexity turns out. So it's exponential in 2 power beta. So that's why our attack cannot scale for large plain text space, but for most of the real world applications it will be the beta will be small, either 16 bits or 32 bits. Good. So I will not get into the analysis of it, and then we implemented the attack. So if alpha is 16 bits, the coefficient space is 16 bits, okay, and there are 10 coefficients, okay. So then and beta is 16 bits, we can recover the polynomial in 4 seconds, and then beta we could not try up to 32 because the symbolic algebra library called Sage that we use ran into error, or it could not handle 32-bit inputs, but for 28-bit inputs, okay. So say if an alpha is we have 32-bit integers and then beta is 28. So we do it in about less than half an hour. Okay. So adversary can be assumed to be quite powerful, you know. So when you're running an operations, it should be fast, but adversary has quite amount of resources and it has time. Okay. So and we all ran our experiments in just on a 12-core machine. And then so number of points, degree was 9, and number of points, as I said, 40 points was enough to recover the polynomial. Okay, and we also experimented on real data, and results turned out to be even better. Okay, so where beta, it was enough to encode the plain text space as 16-bit inputs. Okay, and then coefficients as 32, we could just recover it in less than 2 minutes. So and then one natural fix is our attacks will not work. The PH, we need the exact values of the polynomial outputs. The moment they are perturbed, it will not work. So one obvious strategy is, so here this was P of x1, P of x2, P of x, so on. So you can, in fact, if you want to maintain the outputs also to be sorted, it's enough that, P of x1 is randomly chosen from this input, right? From this range. Then also the order will be maintained, attack will not work. So then we figured out that, this noise, epsilon I, cannot be too large. Because remember, all the P of, so who is doing this, adding the noise? It's the server A. Server A does not have access to it cannot inspect the plain text values. So only the safe error it can add is actually the smallest range, P1 minus P10. The distance is the smallest when between P1, P evaluated at 1 and P evaluated 0. After that, distance goes on increasing. But it cannot see the inputs, right? So it can only add this safe. And then it turns out that if you just take the ratios and assume that xi, xj are large, okay, and then this will be approximately AD into xi power d. Second one will be AD into xj power d. AD will cancel off, and then just extract the dth roots, and you get the ratios. So you will not be able to completely recover xi's, but still you can deduce. So it's a simple attack that works. So looks like there is no fix for this, for their approach. So yeah, sorry for the others. So then just to conclude, so homomorphic sorting and comparison, it's a really open problem, and if one solves it, it will have a very high impact. And then look at alternate methods, So yeah, you cannot do a proper homomorphic sorting or comparison, then just develop but ensure that it's secure, So yeah, I'd like to thank Sonata Software and Professor Devdeep Mukhopadhyay and Shikhar Patranabis. So they are one of the authors. So they hosted them at IIT Kanpur. We presented the method, and then so they seem to agree. And thanks to Professor Mlidhara, for pointing out the results on KMST. So I use sources from these images, thank you. And then any questions? Yeah, they did. They should have done that. I don't remember if they have cited it. That will also have equal computing. Garbage. But then what will the time will also be very symmetric, and it can handle like data sets running into 100. They did unfortunately. Yeah, sorry for the others.
Present the sorting circuit as Boolean yes, so very useful. So you have to provide the data in different forms. You have to provide it in now.
Yes.
It allows you to do the encryption on the input.
Yes.
And then do the calculation encryption.
No, not the typical encryption scheme, but only the homomorphic encryption schemes. Yes. Yeah. Okay. Yes.
So suppose there is a assumption that there is a unit of encryption.
That
is the preserving.
Yes.
The unit of encryption.
Yes.
The original space.
And
there are units which are being encrypted and becomes the encrypted in the encrypted space.
Yes.
And the query is also accessing the same unit.
The query.
So the query is also in terms of the same unit.
Yes.
Suppose you able to encrypt the ABC.
Yes.
And you are able to encrypt A independently, B independently.
Yes. Yeah.
And your query can do operations on A and B.
Yes.
Suppose the encryption takes A, B together.
Oh, okay.
The query is in terms of A and B.
Okay, yes.
How do you ensure the encryption is only on one unit?
Okay. Oh, in fact, like yeah, from the homomorphic computing point of view, that will be very bad. You know, extraction of these components itself is so time consuming that people would prefer to just encrypt each of the A, B, C in a different ciphertext.
Resolve during the query for
No, you can encrypt whatever you want.
how do you ensure the query is also able to resolve the same unit?
Oh no, these are all part of protocol description. It's all prior understanding.
Part of the theory.
No, yeah, theory you can do any, encrypt whatever amount of data. I mean, in whatever unit. Not really in whatever unit, but you can encrypt one bit at a time, or block at a time, or in fact multiple elements at a time. So there are a lot of options at all.
Import
Uh-huh.
to guarantee some consistency between the encryption scheme versus the operation.
No, this will all be part of the protocol description. If you don't follow the protocol, then you will not be able to compute on the encrypted data. Yeah. Yes. Yeah. Yeah.
You don't need to anticipate the query that makes sense.
No. Yes and no, because yes and no, because you in principle you can do any computing, but then again there are like the efficiency aspect also, right? So it's better to have some understanding. Yeah. So, but who gives you, if you encrypt your messages and output to the server?
I understand this.
Yeah.
Tomorrow you want a scale system
Yeah.
where you're looking at a SAP kind of enterprise SAP software
Yes.
running on a huge data.
Okay. Yes.
SAP can do recalculation.
Right. Yes.
So it's claiming that in encrypted space,
Yes.
you can have a parallel computation universe.
Yeah. Yes.
Which SAP starts pulling.
Yeah.
So you can handle
Oh yeah. It can be handled. Yes. Yeah. But again, for the sake of efficiency, people will start tuning a lot, and then if those things happen, yes, you cannot do it. But in theory, in principle, you will be able to. You should be able to scale it to any computing. Yes. But their protocol only works for those cases where you need to sort. Do simple polynomial computation and then sort. Okay. Yes.
I just wanted to understand, on one side you say anti-completeness polynomial,
Yeah.
and when you said you presented an attack, you used so many cores.
Oh, okay.
Is there some parallel computing happening?
Okay. Oh, yeah. So, sorry, I was not very precise with that. So, let me go back there. So, what I basically, no. So, if that was just for theoretical interest, If you want to determine the independent equations, okay, and then so that the guess space, becomes as small as possible, yes, it is NP complete, okay. But then if D in our context is actually fixed. So I just mentioned that result for theoretical completeness, but no way it will have bearing on the on the concrete values. We did not do it optimal. We just searched along a column, but you can do it. Search the whole matrix. Yeah. Yes, please. Multi-key. That's actually a good question. But then someone has to do the comparison and sorting, right? So somewhere it's going to be a bottleneck. Yeah, you said okay. So server B also sees the whole the values in the encrypted form, but ultimately someone should do the comparison and sorting, right? So that will be a bottleneck. Yeah, outsourcing. Yeah, but then a lot of overheads, right? So. Polynomially, what is the polynomial bounded? The complexity? Yeah, complexity wise, but it's just having more parties, then you need to start trust, right? So the more people you give out the keys, then it's problem.
No, I think the multi-key solution that he's saying is let the sorting circuit be evaluated in parallel by both.
Okay, yeah. Oh, okay. Okay, yeah, but then again, not practical, yeah. But your question is good. That why? So, sorry, I don't remember reading that thing. So probably we'll just check it out. Why not MPC, two-party MPC? So will compete with these results? So So still you can make it a non-interactive for the client, right? With the two-party thing.
Just send your inputs.
Okay. Okay. That's a good thing. Yeah. Good. So sorry. Any questions? So then I think, yeah, thank you for it.